All right, so in this section, we're going to look at a few examples of series of functions, okay? Which of course, when you have a series of functions, especially like an infinite series, if you have an infinite series of functions, there's a corresponding sequence of functions, right? Which is the sequence of partial sums of the series of functions, okay? And so anything you can say about the series of functions, really, it's just a statement you're making about the sequence of partial sums. But series of functions are basically like one of the most important examples where we really need the properties of like, uniform convergence, or especially uniformly Cauchy, the uniform Cauchy criterion for sequences of functions. If you could, because that way, with a lot of series of functions, you don't have like a closed form expression for the value, right? You don't have a closed form expression for the limit of the series of functions. So anything you can say about that limit, you have to say by stating it about the sequence of partial sums. And if you don't have access to the limit, then a lot of it, like if you want to say that the series converges uniformly, then you have to basically make the argument that the partial sums form a uniformly Cauchy sequence, okay? For example, so if you wanted to say that the series of functions represented a continuous function, right, then you might want to make the argument that the partial sums are uniformly Cauchy as a sequence, right? So like the most like salient example of series of functions, so far we've seen one important type of series of functions, which are power series, right? Because so it's the sum of a k x to the k, right? So so a k x to the k is a function of x, right? In general, we might consider any series sum of gk of x, where each gk is a function. This series represents a function whose domain is the set of x for which the series of gk of x converges, right? Note that this technically excludes, so there may be some values of x where this series becomes divergent, but it diverges to like plus or minus infinity, okay? Values of x where this series diverges to plus or minus infinity are not included in the domain of the overall function, right? If you try to define a function this way, right? So if we define a function f by f of x equals the sum of gk of x, right? Then values of x for which the sum of gk of x is plus or minus infinity are not included in the domain of f, okay? So of course, we kind of make this distinction of like, okay, in the case, so when this series, if you just look at the series for a particular value of x where it diverges to plus or minus infinity, we like to say that this series still has a value in the sense that the series, or like the series is meaningful in the sense that you can actually consistently assign the value plus or minus infinity to it, right? Because there are a lot of series where that you can't even say that it diverges to plus or minus infinity, like something like the sum of -1 to the n. you know, has no meaning, right? Because the partial sums just alternate between 1 and 0 or negative 1 and 0. And so it's not like it's actually diverging consistently to plus or minus infinity, but it also doesn't converge to any actual number. It just sort of oscillates around. So those are like especially bad series, which like there's absolutely no sensible way to like assign a value to that. But when a series converges or like when a series diverges to plus or minus infinity, we sort of assign the value plus or minus infinity to it. But we would not do that for like if we're trying to use the series to define a function, right? So we don't really want to consider like functions that can actually assume the values plus or minus infinity, basically. Okay, even though like technically it's sort of just a technical thing, but yeah, like by default, we do not include values of x where this becomes plus or minus infinity in the domain of f, okay? Because we're not considering functions that are allowed to like take the value plus or minus infinity at some point in the domain. Okay, so with that out of the way, and also, so like power series are the most important, you know, type of functional series that we've encountered so far, but I'm gonna actually like not really focus on them right now because we're going to give them a full treatment in like later sections. And there's a lot of like kind of, you know, complicated stuff that we're going to do with them. So I'm just going to leave that for later. But let's look at like a couple more examples of different series of functions. Well, one other important example just for like just in general that you might be interested in is a series of the form like an sine of nx, or maybe an sine of nx plus bn cosine of nx. These are Fourier series, right? And so there's a whole like theory, there's a whole like branch of math about this kind of stuff called Fourier analysis, where you know you can take a familiar function or just an arbitrary function, and then you can actually like break it down into a Fourier series. And so all the stuff that we're talking about is like very foundational for that whole process, that whole kind of analysis, you know, because if you want to say that this series actually converges to something, right? And some functions you just define directly through their Fourier series, right? Like you can just come up with sequences for an and bn and then use that to define a function. There are a lot of important functions that get defined that way. So, and in fact, there's something kind of similar to that that we'll see in just a few minutes. It's not going to be sines and cosines, but it'll be something similar. So you'll see. Anyway, so that's a Fourier series. So there are other important, you know, series of functions besides power series, right? Another thing I'll say, actually, just before, you know, one more thing before I move on, is that I think that the ideas that we're introducing right now about sequences and series of functions and how they converge are possibly some of the most important things that you might learn in this class, especially when it comes to applied areas, because like, at least for example in physics, you know, which is sort of, I was a double major in math and physics in college, so I know like a little bit of stuff about physics, like theoretical physics and stuff, and at least from what I remember about it, you know, practically like everything in physics is like some infinite series of functions. A lot of Fourier series or like Fourier transforms, which I guess are not really series, but you know, there are a lot of Fourier series, or just like, you know, in quantum mechanics, you're constantly basically taking like a wave function and then decomposing it as like a sum of some infinite series of like basis functions that are these like special functions. Usually they're like, you know, the eigenfunctions of some operator, or like they're the, you know, they're like the pure energy states for some quantum system or something like that. So then like a mixed state is just some kind of like superposition of these like pure energy states, right? And a lot of the time we allow for those superpositions to be infinite. And so, you know, being able to understand infinite series of functions is really important for those applied areas. And actually the general kind of like theory of, you know, sequences and series of infinite functions, or like spaces of functions, right? Like we saw like C of S, right, is a space of functions. studying the spaces of functions and like sequences and series of functions is like sort of the root or like the basis, the main like thrust of what's called functional analysis. And functional analysis is like very important in a lot of applications, I would say. I mean, of course, you know, from the mathematician's perspective, it's another field of math, and there's a lot of, you know, weird technicalities that mathematicians deal with in functional analysis that most applied people don't really care too much about or think too much about, but they are important because they are some of the, you know, like I said at the beginning of the class, you know, some of the pathological examples, you know, pathological functions or pathological sequences or a series of functions or whatever are some of the most important objects because they are, you know, the challenges and obstructions that they present are sort of one of the primary motivators for the development of a more powerful and more general theory, which then ends up being useful in like more familiar applications too. So anyway, that's kind of my little soapbox there. But so let's just look at a couple examples of series of functions now. So I'm going to actually look at the ones in the book. I'm going to do a little bit more analysis than they do. So here's what they call example 2. Say sum of gk of x is the sum from k equals 0 to infinity of x to the k over 1 plus x to the k, right? So here, gk of x equals x to the k over 1 plus x to the k, right? So, you know, I mean, this is just, I mean, they just kind of like write this down as an example of a series of functions. It's not a power series, right? Because this is not, gk is not a constant multiple of some power of x, right? It's something totally different. So this is not a power series. That's actually really important. Like, I know there's an x to the k here, but there's more than that. So it's not, this is not a power series. Although you could rewrite it as a power series. So as it's written, could be rewritten as a power series. I will say that. It's not actually even, it's not even that hard. But anyway, so the series clearly converges pointwise for absolute value of x less than 1 by comparison to just the geometric series, right? Because since x to the k over 1 plus x to the k is at least, oh, let's just say, yeah, let's just consider positive values of x. Okay, let's not even deal with negative values of x for now. So say, you know, x is in 0 infinity. Okay. But so then it converges for x less than 1, right? Since this is less than x to the k. On the other hand, it diverges for x greater than or equal to 1, oops, because for these values of x, for these values of x, x to the k over 1 plus x to the k does not converge to 0 as k goes to infinity, right? So one basic criteria, like one important like basic requirement for a series of numbers to converge is that the terms have to approach zero, right? Because if the terms don't approach zero, then like the adjacent partial sums will not be getting closer together, right? So there's no way that it'll be a Cauchy sequence. So the terms of a sum have to approach zero for the sum to converge. If these don't approach zero as k approaches infinity, then that's a problem. So this diverges for x greater than or equal to 1. It does converge for x less than 1, right? Now I'm actually going to show, so let's show that the partial sums, so let's say fn of x equals the sum from k equals 0 to n of x to the k over 1 plus x to the k converge. Let's show they're uniformly Cauchy. Are uniformly Cauchy on 0a for a strictly less than 1. Okay, so it's actually the case that fn, these partial sums do not form a uniformly Cauchy sequence on the whole interval 0, 1. So fn are not uniformly Cauchy on 0, 1 open. Okay, they are not uniformly Cauchy, but, and you can actually tell just because like they have to diverge when x is 1, right? They end up diverging, so it kind of makes sense that they wouldn't be. But if you just chop off some piece of the end of the interval here and have some a strictly less than 1 and then look at that closed interval, they actually do they are uniformly Cauchy on that. So to see this, oops, like, so, okay, let epsilon be greater than 0. Then what we want to look at, right, is the series, or the difference fn of x minus fm of x is the sum, the absolute value of the sum from k equals m to n. This is for n greater than m, greater than or equal to m, of x to the k over 1 plus x to the k. Since all the terms are positive, we can just drop the absolute values. So this is the sum of x to the k over 1 plus x to the k for k equals m to n. And then this is less than or equal to, right? Like I was saying, since 1 plus x to the k is bigger than 1, this is just less than or equal to the sum from k equals m to n of x to the k, right? Which in turn is less than or equal to the sum from k equals m to n of a to the k, right? Which equals a to the m times the sum from k equals m to n of a to the k minus m. And then we can re-index this series, right? This is the same thing as a to the m times the sum from k equals 0 to n minus m of a to the k, right? And then this is less than or equal to, well, it's really strictly less than a to the m times, like, this is just a partial sum now. This is like the first n minus m terms of a geometric series, right? So if you just add in the infinitely many other terms, that this approaches 1 over 1 minus a, right? So this is a to the m over 1 minus 1 over, yeah, a to the m over 1 minus a. So choose m, or sorry, choose n such that a to the n over 1 minus a is less than epsilon, right? This is possible since a is less than 1, right? So because so this like because this sequence, as if a is a constant less than 1, as capital N approaches infinity, these values approach 0. So they eventually have to get smaller than epsilon, right? So so if you choose capital N this way, then for all n greater than m, greater than or equal to m, greater than capital M, we have absolute value of fn of x minus fm of x is less than or equal to a to the m over 1 minus a, which is in turn less than or equal to a to the capital N over 1 minus a. Well, really, that's just strictly less than, since m is greater than n. And then this is less than epsilon, right? This was from our earlier work, right? On the previous page here. That's what we showed, okay? So that shows that it's, so Fn is uniformly Cauchy on 0a. And would you look at that? That means that, so if we define f of x equals the sum from k equals, let's say, is from 0 to infinity of x to the k over 1 plus x to the k, this is continuous on 0a because each gk is continuous. So each partial sum, well, Fn, right? Fn, which is the sum from k equals 0 to n of gk, right? If you add up a finite number of continuous functions, you automatically get a continuous function, right? So since each term, right, x to the k over 1 plus x, I'm saying, so gk is this, right? So this is clearly continuous. So then a finite sum of those is also continuous. So each partial sum Fn is continuous on 0a, since Fn is uniformly Cauchy on 0a, it converges uniformly to f on 0a, so f is continuous on 0a. Also notice actually that since a was an arbitrary number less than 1, this actually shows that f is continuous on the whole 0, 1, actually. So that's a weird, like, kind of a strange trick, or I don't know, it feels like a trick, I guess, maybe. This actually means f is continuous on 0, 1. Okay. So anyway, because a was arbitrary between 0 and 1, basically. So yeah, you can see actually from this, really, you can see the power of the theory, right? I mean, you can see the power of the concept of uniformly Cauchy sequences and series, because we have no idea what f of x actually is. I mean, like, honestly, off the top of my head, I'm not actually sure. I think there actually might be a formula for it, but it's not easy. It's not easy to find. So, you know, we didn't even need that at all. We don't need a formula at all. We're able to do a lot of stuff. We can show that it's continuous because we can show this series converges uniformly, at least on this set here, right? So I think that's pretty cool. And actually, so really quick, okay, I'll try to make this as quick as possible. So the other example they give was example 3. So they say, so let g be the function, and then they give a graph of it. So it's like this. Oops. Right. And so it goes between, yeah, so this is 1, 2, 3, 4, 5, 6, right? And it's always going up to 1 and then back down to 0. This is -1, -2, -3, -4, so on, right? So it's just kind of these lines of slope plus or minus 1, and it bounces back and forth like this forever. So that's G. Then define, whoa, define. Innovative. So then define Gn, right? So define Gn of x equals G of 4 to the n x. So basically when you take G of 4 to the n x, all that does is it like scrunches the wave like way closer together by a factor of 4 to the n, basically, right? It squishes it by a factor of 4 to the n. So it increases the frequency, right? So basically Gn has frequency 4 to the n times the frequency of G, right? Sorry, maybe I should actually say times, right? So it's much higher frequency. Then define, like, let's say, yeah. So then take f of x equals series of 3/4 to the n Gn of x. Okay, so since well, let's see, this is from n equals 0 to infinity. Since absolute value of Gn of x is less than or equal to 1, it's straightforward to show Fn, right? If Fn, these are the partial sums, is uniformly Cauchy on R. And so as a consequence, right, clearly each Fn is continuous, again, just because G is continuous, so Gn is continuous, and then 3/4 to the n Gn is continuous, right? And then any partial sum is continuous from that. So all the partial sums are continuous, and the sequence is uniformly Cauchy on all of R, actually. And because of that, so F is continuous on R. You can note that actually F is automatically periodic with period 2, just because that's the largest period out of all of the G's, right? Like G0, yeah, G0 is just G. So yeah, F has period 2. Not that that really matters, but whatever. So F is continuous on R, but it turns out F is nowhere differentiable. So, there you go. This is like a function that it's important to be aware exists, right? Or at least some function like this. Okay, there are a lot of examples of functions that are continuous everywhere but nowhere differentiable. But the knowledge that those exist is like very important, okay? Because otherwise you might be assuming that a continuous function automatically has a derivative at least somewhere in its domain, and that's just not true, okay? So in fact, it turns out that like almost any example of a continuous nowhere differentiable function must be constructed as like some kind of infinite series like this, okay? At least all the like sensible, all the sort of like reasonable examples of this are constructed as infinite series. So you can also see like, again, why this is important. it gives us a way to construct these like crazy pathological functions that have all sorts of like interesting properties that, you know, we probably wouldn't really be able to like find without the technology of like infinite series of functions and uniformly Cauchy and stuff like that. So anyway, that's it for this video. It ended up being a little bit longer than I planned, but hope you enjoyed it. And in the next one, we will just prove some basic stuff about series of functions when the partial sums are uniformly Cauchy, and then we'll look at the Weierstrass M test.